Hi, I want to go through the analysis for the stopper lab for this first experiment, just so that we have an example here. And this example includes something that's a little bit interesting in terms of the manipulation of the equation, and of course, the manipulation of the data. So in this experiment, we're looking at the tension force that's being applied to the string. And we're looking at the string length as being the independent variable that we change. And the stopper is moving at a constant frequency based on the running of a metronome in the background to set how fast or how long it takes for each cycle. That's set at 140 beats per minute. And the mass is swung in a horizontal circle at 6 different radii. So here are the radii in centimeters. And the tension force on the string is measured by a force sensor. And we have the values for those forces here. So to start with on this, I want to think about what's the relationship that I expect between tension force and string length. And I've put that onto, I've written that out here. The measured values that we have are the radius on the force. So the relationship that we're looking at is going to be F is equal to mv squared over r, the expression for centripetal force. An important thing to note here is that this, we might be saying, oh, we've already got a relationship between F and R. However, we have to make a careful note, and this is the thing that's important and special on this one. Velocity is not a constant here. The thing that we're holding constant is the frequency, but since we're changing the radius of the motion, the velocity is going to be changing for each of the trials that we have. So we need to manipulate this expression a little bit until we have a constant times the radius or a constant times some power of the radius. That's not so hard to do because we have an expression for the velocity in terms of the frequency. So I substitute in 2 pi r times f for the velocity. Squaring that and manipulating it, we end up with 4 pi squared times m times the frequency squared times r. And we have our dependent variable here, f, our independent variable r, and I'm just going to go through and check to make sure that all of the other terms that are multiplied here that are included in this expression are constants. So in this case, the 4 is, pi obviously is, the mass of the stopper is, and the frequency is. So we actually already have a linear relationship here. F is equal to a constant times the radius. And so our expression has already been linearized. We'll use on the y-axis the force, on the x-axis the radius, and then we expect that the slope of this proportional relationship will be 4 pi squared times m times f squared. And just I'm gonna skip ahead on a step here that we'll use after we've graphed the data. But since we have a measured value for the mass of the stopper, and we have a measured value for the frequency in beats per minute, and we can convert that to revolutions per second, we can actually find what we will expect exactly for a value of the slope. I've left the units off here. The units are going to be kilograms per second squared. It's kind of a weird unit, but this is going to be what we would expect to get for our slope. Continuing on with the analysis, I have that theoretical relationship that I'm looking for between the force that we're measuring and the radius. It's already linear. And so now it's time to plot the data and fit a regression line. I am looking for the force versus the radius. So that's going to be pretty straightforward here. Let's go back up to the data. And I'll pull open a Logger Pro window. For the x value, I'll do that as my radius of motion. We'll give it the value r, and units of meters would be best here. And I'll put in the values. So I have 0.195, 0.317, 0.475, oops, mistake, x, B 0.475. 0.605, 0.755, 1.005. So there's the different values for my radius. The force, we'll call this the centripetal force. F units will be in newtons. And then we have, well, this one I might be able to just copy and paste because the units are already correct in the table. Copy, paste. Oops, pasted not quite right here. Copy, cut, and paste. All right, so there we have our data. Let's auto scale that and then change this a little bit so that we have the 0. It's definitely looking relatively linear. That's good. And so now the last thing I'm going to do is I'm going to add lines of fit to this. So I'll do 2 different fits, or 2 different lines on here. The first one that I'll do is I'll do a linear regression. So this is a fit to the data that I have, right? So my linear fit here goes through the data points relatively nicely, some above, some below. It looks like it's coming close to going through the origin, which is where it should be going through for a proportional relationship, but not exactly. And the second thing that I'll add is I'm going to insert a model. So I'm going to go to Analyze, Model. And this is where I'm going to put in the model proportional relationship here. So from that calculation before, I know that I expect the value of the slope of that proportional relationship to be 3. So here, that proportional relationship, I'll put in 3.0 and OK. And now I have a second curve on there that's this proportional relationship, A times R, where A is equal to 3. Just going to make a quick change to this so that it looks different. So that we have, say, a red line here for the model and a black line here for the fit. And you can see that both the model and the fit seem to be reasonable. But we really should have a look at the error bars to really get a better sense of that. Does this model fit as well to the data as the regression line that's the line of best fit? In order to do that, we'll want to add a couple more columns here. So I'm going to go back to my data, and I see that I have uncertainties in centimeters for the radius. So I'm going to add a new manual column. So for, I'll call this uncertainty R, or radius. Go UNC R, units of meters. And I'll put in those values, making sure that I convert them. They're a little bit different here, so I have to be careful. I can't just use a constant. And then I'll go in the options for R, and I will say I want error bars on there, and I'm going to use the column uncertainty radius. Okay. So tiny little error bars there. That's not giving me a lot of confidence that my values are okay yet. So let's see what we have for the force uncertainty. So we'll do a new manual column, and this will be uncertainty force, UNCF, and also in newtons. And I'll copy those numbers over. And the last time I pasted, it didn't paste exactly right. Let's see what happens now. Still didn't paste quite right. It's frustrating. And now I'll do the same thing to add that uncertainty to the force column. Options, error bar calculations, use columns, uncertainty force. Oh, okay. So we do have quite a bit of uncertainty on the force there as that was measured. And this is going to give me a lot more confidence. So when I look at that red line, the error bars do actually include that line. So I can feel pretty good about the fact that, let me move this down to the bottom, that the line of best fit is the best fit to the data, but this model equation does seem to be consistent with the data because all of the points do include that model fit. I might do one last thing here with some fits. I might add a maximum gradient and a minimum gradient and do some uncertainties on my measured value for the slope. So let me go into Analyze, and let me do a curve fit. This one's going to be a manual fit. So we'll do the linear fit, and we'll try it. And we'll switch it over to manual. So we have that manual fit now, but I'm going to set it so that I can enable that line drag. I'm also going to switch this one over to, I think, I'll do blue for the maximum and minimum. So with the line drag here, I'll try to place that. Let's get the minimum value for the gradient. So all right, that's about to fall off of the error bar here. So we'll use that. So my minimum slope is 2.054. My M fit. All right, that then down is 2.507. And my N max. Let's do the handlebars again. And we'll come down here maybe, and up here. Oh, we're about to go off of the top of, we've lost one of our points. So there we go, we fit all of our data, 2.917. So if I want to do an uncertainty calculation on this, I'm going to remove that manual fit. It's starting to get a little bit busy. If I want to do an uncertainty on this, I would say that my value is 2.507 plus or minus, and let's see, so we have 2.917 minus 2.054. Maybe I just round this to one significant figure because it looks like it differs in the first, or two significant figures because it differs in the first decimal place. So I have 2.9 minus 2.1, so that's 0.8. So we'll do plus or minus 0.4. And so I should probably write this as 2.5 plus or minus 0.4. And that's going to be newtons per meter. So now I have a fit value for the slope of the line of best fit. And I can do some manipulation with that as well. Let's see how we're doing with the recommended analysis. With the recommended analysis, let's see, we have the relationship that we expect. It's linearized. We've plotted the data. We have a regression line. We found, we haven't used this value for the slope to find a theoretical value, or sorry, a model, a data value for the mass of the stopper. So let's do that quick. We have 2.5. So we have 2.5, this is my slope, plus or minus 0.4 newtons per meter. I know that the value of the slope should be equal to 4 pi squared times mass times frequency squared. So let me just, I won't worry about the error bars right now, or the uncertainty right now. So I have 2.5 is equal to 4 pi squared times m. We're looking for the experimental value here. And then the frequency was what? I think the frequency was 2.3 revolutions per second. 2.3 squared. Quick use of the calculator for this one. So we have 2.5 divided by 4 divided by pi squared divided by 2.3 squared. And I get m is equal to 0.01198, which with significant figures, I'm going to round to 0.012, which is the same thing. So that's going to be in kilograms. And so that's the same thing as 12 grams, which is not quite the same as 14 grams. But if I wanted to find a percent difference, it's 2 grams different on 14 grams. So that's 15% different. So this is a 15% difference from expected. And I suppose that's not really so bad. 0.4 over 2.5. So the uncertainty that we have, the percent uncertainty that we have on this value is actually 16%. So these are just barely consistent with each other. We have a 15% difference between the 12 grams that we measure and the 14 grams of the stopper. But we have an uncertainty on the mass of 16%, and that's not even including the uncertainty here, which is another 3%. So there's probably about 20% uncertainty on our values, and the percent difference from the experimental value is only 15% or so. So those are consistent, backing up what we see from fitting a proportional relationship that we expect to the data. We put a model onto the graph. We've added the error bars. We found maximum and minimum gradients. We have the uncertainty of the best fit slope. We found a stopper mass. I didn't mention it, but we just talked through that 20% uncertainty. Maybe it's 19%. So we've talked a little bit about how the experiment agrees with theory and whether it agrees with the, we didn't talk about whether the experiment agrees with theory. This experiment does pretty clearly agree with theory. We do have the line of best fit, doesn't quite have a 0 y-intercept, but when you add a model that is proportional, it fits very, very nicely with the data. This point might even be considered an outlier. If we ignore this point and look at the model falls well within the error bars. It's really only this one data point that we have that falls outside, which out of 6 data points, it's not that surprising to find one point that doesn't fit well. So it does look like the model relationship that we have from theory, this f is equal to 4 pi squared m f squared times the radius, fits very nicely. And the value of the slope, 2.5, is nearly consistent with what we find for the line of best fit. I might go one step further with this. I might say, let's assume that we have a proportional relationship and fit the slope. So I could reselect this data and I could say, let's not fit it with a line, but let's actually do a curve fit that's just a proportional relationship and see what the fit is. When I do that, the value that fits to the data is 2.8, so even closer to what we were expecting of 3. So I've got to be feeling pretty good about how this model, seeing linear data that's proportional, I've got to feel pretty good about that, so that this idea that F is equal to mv squared over r is a good relationship, the centripetal force. is consistent with that equation. And I've also got to be feeling good about the way that I measured this, because the expected value of the slope is within the uncertainty. Moving forward with this experiment, I know that most of the error that I have comes from measuring the force. That's really not surprising. When I collected the data, I saw that there's a lot of noise in the force going up and down, in part because I have to keep swinging this. The air resistance is causing there to be energy lost from the system. I have to keep putting energy back in. So it's not exactly uniform circular motion to begin with. So I'd really look to changing the experimental design so that I can bring down these error bars for the force. Once I've brought down the error bars for the force, that would give me even more confidence or reveal some very slight deviations from the model. Anyway, a full analysis of the data that we collected for this. There's a couple more experiments here. I hope that you can complete that analysis in much the same way for those two. Put some of that into writing, talk through it with each other, and enjoy.